Hello, good afternoon, and good morning. Welcome to IEA Bioenergy webinar series. Today's webinar is entitled Novel Opportunities for the Development of Biorefineries, Biocarbon to Chemicals and Fuels by Integration of Biorefineries and Green Hydrogen. My name is Chiara Benetti and I welcome you on behalf of ETA Florence Renewable Energies, technical organizer of this webinar. The webinar will be moderated by Isabella De Bari and Aristide Giuliano from Enea, Italy. And the speakers of the webinar will be Nicola Pierro from Enea, Italy, Kostas Triantafillidis from the University of Thessaloniki, Greece, and Abhijit Dutta from NREL, USA. As usual, you have the possibility to drop questions by using the Q&A tab that you can find at the bottom of your screen. Our speakers will reply to your questions either by typing the answers directly in the Q&A tab or at the end of all presentations by replying to you orally. As usual, the recording and the presentations of this webinar will be available on IEA Bioenergy website from tomorrow on. Please use the Q&A tab for questions and do not use the chat box. Just use the chat box for greetings. I think that's all from my side. I'll give the floor to Isabella and enjoy the webinar. Thank you.
Okay, thanks, Chiara, for your kind introduction. I'm going to share the screen. Can you see my screen?
Yes.
Yes. Okay. So good afternoon, everybody, and welcome to this webinar. In this short introduction, I'm providing just some framework elements to the webinar. Production of biofuels and chemicals through biorefineries can provide a contribution to the decarbonization strategies. And general advantages of biomass lie in the capacity to absorb carbon dioxide from atmosphere to replace fossil fuel and chemicals and to produce carbon that can be stored. As for the refinery produce energy product and mainly building blocks for chemicals, the biorefineries produce alternatives to fossil products or terpene products to biomass conversion and fractionation into platform molecules such as sugars, syngas, fatty acid, bioaromatics, and so on. In Europe, trajectories for biofuel derive from the Renewable Energy Directive and include the replacement in 2030 of 29% final energy consumption in the transport sector with renewable energy, with a share of 5.5% biofuel and 1% renewable fuels of non-biological origin, namely synthetic fuels produced from hydrogen. 2 EU regulation, the ReFuelEU Aviation and FuelEU Maritime, set also ambitious targets in terms of fossil fuel replacement and reduction of emissions. A similar push to increase the renewable carbons in chemicals and materials derived from the Green Deal targets, namely 20% of renewable carbon in chemicals and plastics. Globally, approximately a quarter of renewable electricity generation would be used to produce the green hydrogen, around 200,000 kilotons per year needed by 2050. Hydrogen is included in many national strategies to decarbonize the industrial civil sectors and also for green mobility. Considering the huge amount of hydrogen currently needed in the oil refinery, the use of hydrogen as chemical reactant could be similarly considered in biorefineries to convert many renewable carbon sources. One main issue in the decarbonization strategy to hydrogen is obviously the economic sustainability of the hydrogen production, storage, and transport costs. And the major part of the hydrogen currently used in the industrial sector is produced through the steam reforming of methane, with a cost around €2 per kilogram. The combination of different electrolyzers with different sources of renewable electricity offers some options to produce green hydrogen with cost of at most 2 times higher than hydrogen from steam reforming. Biohydrogen can be produced from biomass through many thermochemical and biological pathways, with production costs ranging from €3 to €6 per kilogram, depending on the final purity level. But if biomass can be a source of hydrogen, more interestingly, biomass and biomass-derived streams can be converted to many final bioproducts and downstream products by using green hydrogen, similarly to what's substantially happening in your refineries. In fact, biomass contains 35 to 40% oxygen, and green hydrogen can act as a reactant to reduce the oxygen content, mainly through hydrodeoxygenation processes. One major question is in what condition the use of hydrogen in biorefinery can be sustainable. Use of hydrogen in biorefineries could regard the conversion of both gases and liquid products and intermediates. Biogas upgrading to biomethane through CO2 conversion is a widely investigated process. More complex is the conversion of CO2 to DME via the methanol route or further bioproduct with a higher number of carbon atoms. Gasification of biomass could be an option to produce both maritime and aviation biofuel and the syngas upgrading in terms of internal CO2 hydrogen optimal ratio. The largest share of biofuels in the short period will be likely supplied by HVO or alternative bio-oils with a similar composition, like, for instance, microbial oils. The hydrotreatment of this feedstock could provide both diesel-type product and sustainable aviation fuel. Bioalcohol condensation and hydrotreatment is a pathway to synthesize paraffins for aviation biofuel, and hydrothermal liquefaction of biomass is an option to produce bioaromatic and biojet components, and this topic will be further discussed later in this webinar. Besides fuels or hydrogenation processes are needed also to produce many chemicals such as bioaromatics or many building blocks like BDO or sugar alcohols. As a part of the current IEA Bioenergy Task 42 triennium, ENEA produced some case studies for the integration of green hydrogen in selected biorefinery. The methodology we have developed is based on techno-economic assessment, and data were retrieved from web-GIS portals of existing biorefineries and the local biomass availability, together with the local production of green hydrogen from solar and wind farms. Several web-GIS national portals are available that could provide data on the local biomass supply chain for existing biorefinery or potential future plans. The global biorefinery portal that will be presented later in this webinar provides data on existing biorefineries infrastructures, technologies, plant sites, location, feedstock, and product, and finally the status of operation. 1,119 plants are currently mapped in the web portal, and 76% are bioenergy, biofuel-driven biorefineries. At the moment, only 9% of the biorefineries planned based on chemical technologies in the database use hydrogen. So in conclusion, key elements of this webinar are georeferenced biorefinery database could be a dynamic observatory containing useful data to monitor these sectors and also to support the assessment of a novel technological scenario. The current items include 21 plants using hydrogen as reactant, with the sites ranging in 200 to 1,000 kiloton per year, mainly HBO and SAF, and with a draft estimation of hydrogen requirement in the range 300-600 kilotons per year. Based on the biofuel trajectory at 2050, green hydrogen needed to produce drop-in biofuels and hydrogenated biochemicals would be at least 20-30 times higher than the current estimation for the plant included in the database. And this could be coherent with the overall hydrogen production scenario. But these need to be supported by techno-economic evaluation and analysis of the local integration of renewable sources, as will be presented by the next speaker. So thank you for your attention, and I give the floor to Aristide for his presentation.
Thank you, Isabella. So, can you see?
Not yet, Aristide.
Yes?
No, try sharing again, please.
Okay.
Okay.
Can you see?
Yes.
Perfect. Thank you. Thank you, Isabella. Hello, everybody. I'm Aristide Giuliano, Enea, Italy. Today, to present an IEA Bioenergy Task 42 special project on the integration of biorefineries, existing biorefineries, and green hydrogen. So, why biomass and hydrogen? As seen in the previous presentation, in the next future, green hydrogen from water electrolysis using variable renewable energy will play a central role in the global energy scenario. This energy carrier, the hydrogen, can be used to several applications for the transition to a complete green economy. An opportunity consists in the conversion of renewable carbon sources to chemicals and fuels. An important thing is that biomass is the only renewable carbon source that can reduce CO2 to obtain it. Furthermore, biomass and green hydrogen have both a large dispersion on a territory. This specific characteristic can be another point to be exploited for their local integration. The special project aims to assess potential integration between bio-based processes and green hydrogen production using variable renewable energy during the overload hours. About the methodology we used, starting by individuation of existing or under construction biorefineries, the technology assessment was useful to estimate the CapEx and OpEx of the plant and also the green hydrogen requirement. So, how much green hydrogen I have to produce locally in the selected territory by using the available renewable sources? And what is the green hydrogen production cost to supply the biorefinery, considering production, storage, and the hydrogen transportation costs? Finally, by matching of all of these costs, we can estimate the final product production cost, and so the potential impact of the green hydrogen supply cost on the total product cost. An important aspect is considering also the green hydrogen transportation cost from wind or solar farms to the biorefinery. To calculate the green hydrogen cost, we used perspective data from literature. In particular, we divided costs for production of hydrogen, hydrogen storage, and hydrogen transportation costs, considering three alternative options. As compressed hydrogen or liquefied hydrogen for the storage, and a transportation by a new dedicated hydrogen pipeline or compressed hydrogen transported by truck. A case study overview. The first one was for two small biogas upgrading plants in Italy, producing biomethane, using green hydrogen for the catalytic methanation process. The second one in USA for the production of 550 kilotons per year of renewable diesel using vegetable oils and other lipid sources as stock. The third one, the potential direct lignin hydrodeoxygenation producing now 9,000 tons of phenols and other aromatics. Coupling that to a second generation ethanol biorefinery in Brazil. And the last one, sustainable aviation fuels production from bioethanol for a biorefinery under construction located in Australia. So quickly, for the biogas upgrading by methanation, we choose two typical size biogas plants, one in Melfi and one in Banzi, in Basilicata region in southern Italy. About the technology, we assessed a techno-economic analysis starting from a purified biogas derived from the anaerobic digestion, obtaining 150 kilogram per hour of biomethane, purified by a conventional membrane technology. To make that, 72 kilogram per hour of green hydrogen were necessary. So we have about a half kilogram of hydrogen per kilogram of biomethane produced, and a production cost without considering the green hydrogen of about 0.2 euro per kilogram, but we need 0.5 kilogram of hydrogen per kilogram of biomethane. So where we can find it, there are these capacities of the wind farms in Melfi and Banzi, and assure overproduction of renewable energy in both municipalities. So we can consider a potential green hydrogen production of 6,000 tons per year in Melfi and 1,600 tons per year in Banzi. This quantity, these values are higher than the green hydrogen requirement of the methanation plants. So this matching between a local bio-based process and potential green hydrogen is feasible. And with more or less 10 kilometers for the distance between biogas plants and the wind farms, a green hydrogen production, storage and transportation cost in a range from 4 to 9 euro per kilogram of hydrogen was calculated. In the second case study, hydroprocessed esters and fatty acid production from oils and lipids. For this case study, we choose from the Biorefinery Atlas, a biorefinery in USA, in North Dakota, Dickinson. processing 700,000 tons of oils. The technology assessment was on the catalytic hydrogenation with the recovery of unreacted hydrogen and valorization of the purge gases producing electricity. A drop-in diesel can be obtained finally. Further, we studied the effect of 7 different feedstocks, common vegetable oils, microbial oils from a second-generation sugar platform, waste cooking oils, and lipids from algae. Really, the process performances didn't change a lot. So a medium final yield of 80% can run well, with a nitrogen requirement of more or less 5%, arriving to a green diesel production cost lower than €3 per kilogram, depending a lot by the raw material, the oil purchase price. This without the green hydrogen supply cost again. So on the territory for the local integration, we know in North Dakota state the renewable energy sources are super abundant. So we can suppose the overproduction. In particular, there are 2 wind farms in a radius of 40 kilometers with a total capacity of 300 of megawatts. For those we can get those we can get 21,000 tons of hydrogen per year, so less than the biorefinery needs. And so this matching is not feasible, unfortunately. But you must not lose hope, because widening the distance range from 40 kilometers to 100 kilometers, we can push also the energy production from other 3 wind farms, producing globally 40,000 tons of hydrogen per year. And so, also in this case, we can consider the matching feasible at a cost for the transportation of green hydrogen higher, resulting a final green hydrogen supply cost of more or less €2 per kilogram. About the third one, the lignin hydrotreatment. From the Biomass Atlas, we individuated in Brazil a second-generation ethanol biorefinery, having as a waste about 70,000 tons per year of lignin. So we built a lignin process conversion by direct hydrodeoxygenation, obtaining alkylphenols and DTEs, aromatics. From process design and CAPEX and OPEX analysis, a final alkylphenols production cost of 1.4 to 3.8 euro per kilogram was found without the cost of hydrogen again. In this case, a wind farm 300 kilometers far was considered with a capacity of 220 megawatt, producing potentially about 12,000 of tons of hydrogen per year. And so, also in this case, the matching is feasible. The green hydrogen cost we calculated is in the range 2.8 to 5.4 euro per kilogram. So the last one, an under construction project, Ulysses, from the Biorefinery Atlas in Australia. converting second-generation ethanol by dehydration, oligomerization, and hydrogenation to 19,000 tons per year of sustainable aviation fuels. In this case, a nitrogen requirement very, very low is necessary, only 0.01 kilogram of hydrogen each kilogram of SAF at a production cost lower than €3 per kilogram. The green hydrogen supply was considered thanks to a solar farm 30 kilometers far, producing potentially about 3,000 tons per year of green hydrogen, covering the small green hydrogen requirement. The case study for this local integration can be considered feasible, and the calculated green hydrogen supply cost was in the range 2.7 to 5.7 euro per kilogram. So now we can summarize the case study results. In particular, the green hydrogen cost for the biomethane production was the potentially highest due to the small quantity of hydrogen to store and to transport, and so due to the economies of scale. Then in the USA case, to produce green diesel, also considering the wind farms installation cost, we can have a green hydrogen cost about €4 per kilogram in perspective. The high quantity of hydrogen to feed the biorefinery allows to consider the compressed hydrogen pipeline as the optimal one. Then, for the conversion of lignin from a second-generation ethanol biorefinery in Brazil, a liquid hydrogen storage and transportation was found as the optimal choice. Finally, the production of sustainable aviation fuel by an alcohol-to-jet process in Australia, liquid hydrogen could be transported to the biorefinery. Here, a summary of the specific requirement of hydrogen. We can see the conversion of CO2 has to pay more hydrogen, about 50% of the biomethane produced. Very low quantities are necessary for the green diesel and sustainable aviation fuel production. Here we can see the medium market price of the target product studied, and we can see that biomethane converting CO2 of biogas is not economically sustainable due to the green hydrogen supply, essentially. Further, good results for green diesel and alkylene phenols production. SAF seems not ready for an economic convenience, also without depending by the green hydrogen cost. Then we can calculate the impact of the green hydrogen cost on the final production cost, again to high values for the biomethane synthesis. In conclusion, in this project, several case studies were assessed and potential matching between bio-based processes, existing biorefineries, and green hydrogen were established as feasible. For the local green hydrogen production costs, lower than €6-8 per kilogram were estimated. Where a very different green hydrogen supply cost impact on the total production cost can be found changing the bio-based process, essentially. Then we can assume that the local integration of biorefineries and green hydrogen could represent an optimal opportunity to make the hydrogenated bio-based products 100% renewable. In the future, also other case studies, biomass supply chain and green hydrogen supply chain optimization will be carried out, I think, during the next Trinium program of the IEA Bioenergy Task 42. And thank you. So, Nicola, the floor is yours. Thank you.
Thank you, Aris. I'm sharing my screen. I hope, do you see my screen? Okay. Just a second, please. Perfect. Hello, everyone. I am Nicola Pierro, researcher at INEA, and I'm going to present the IEA Bioenergy Task 42 web-GIS portal Global Biorefinery Atlas. But first, what is a biorefinery? According to Task 42, biorefinery is a sustainable processing of biomass into a portfolio of marketable bio-based product, food, feed, chemicals, and bioenergy. There are many typologies of biorefineries. Energy or biofuel-driven biorefineries, where biomass is primarily used to produce biofuels, power, and/or heat, and processed residues are sold or even further upgraded to value-added bio-based products. And the product-driven biorefineries, where biomass is a typical fractionated into a portfolio of bio-based products, with the focus being to derive the highest economic value. The residues generally are used for power and/or heat production. The idea of creating a database on biorefinery dates to the triennium 2016-2018, where within the work bioeconomy and biorefinery strategies in the EU member state and beyond, it was this one task concerning the assessment of biorefinery in Task 42 members country. A survey has been created and submitted to various stakeholders. The actors involved in this activity were the Joint Research Center of the European Commission, the Bio-Based Industries Consortium, now called Circular Bio-Based Europe, and the IEA Bioenergy Task 42. This work allowed the census of 62 plants divided in commercial plant, demo pilot plant, and flagship plant. In the past triennium, it was decided inside the Task 42 to dedicate an activity aimed at creating a harmonized database of biorefineries from data deriving from the various database and its publication and sharing through a web-GIS portal. There are several databases regarding bio-based industries, biofuel plants, and biorefineries available online, but they aren't harmonized each other due to different classification applied, different name of process, etc. The main scope of this activity was to harmonize this data. The web-GIS portal was made public at the end of 2022. First of all, we started with the analysis of this database available online, like the National Biorefinery Database and integrated biorefinery maps elaborated by the Department of Energy of the United States, the GRC, the Biorefinery Industries and the Biorefineries Distribution in Europe, available by the Data M portal of the GRC, the BBI biorefinery maps elaborated for Europe by Novia Institute in 2017, the IEA Bioenergy Database elaborated by the Task 49, the Biofuel Digest Database, and other European, international, and national projects. From the analysis of this website, a database structure was elaborated where the information connected were the name of a plant, the country, the city, the owner, the production capacity, the TRL, the feedstock, the products, the refining technology, the status of the plant, the starting year, the source of the information, and the geographical coordinate of the plant. In order to classify this information, it was decided inside the task 42 to apply as a classification the classification elaborated under the European project EU Biorefinery Outlook 2013. In this classification, biomass are divided into main classes, primary biomass and secondary biomass. In each class, there are several categories. For example, for primary biomass, there is aquatic biomass, lignocellulosic from cropland and grassland, and so on. For conversion process, we have a biochemical class, chemical class, mechanical and thermomechanical, thermochemical class, and for product, there are chemicals product, materials product, food, animal feed, and energy. In order to consider the flexibility of the biorefinery in using different biomass classes on different process classing or in producing different class of product, three new classes have been added, in particular multi-feedstock for biorefinery using both primary and secondary biomass, multi-process for biorefinery using the two or more process of different class, and multi-product for biorefinery producing two or more products of different class. All information collected and harmonized has been uploaded to the web-GIS portal. Now I'm going to show the main tools of the web-GIS, which are the tools layer, the tools graph, and the tools search. Now I'm going to show the portal with the browser. I hope do you see my screen. Now I'm using Mozilla Firefox as browser, but you can use any type of browser. When the main page is open for the first time, the web portal disclaimers appear. The web portal disclaimer can be opened also with these tools. The tools are located into the left toolbar. Through the tools layer, it's possible to change the base map of the web-GIS. The default base map is the classic OpenStreetMap, but it's possible to change to aerial. In these tools, there is also the function setting. With this function, it's possible to display feature on the map classified for feedstock, for example, production capacity, TRR, refining technology, product, status. As you can see, the legend change, starting year of the plant. And there is also a function add a layer where it's possible to add to the map a web map service or a KML file from your personal computer. The tool graph, through this tool, it's possible to view histogram showing the classified information. For example, the current histogram shows the distribution of biorefinery by feedstock class. If we come back to the tool layer and select, for example, a product, the histogram change. Now the histogram shows the distribution of the plant by classes of the product. By clicking on the chart menu, it's possible to view in full screen this histogram, download histogram as image, or download this data as CSV file or Excel file. Through the tool search, it's possible to select the feature based on the classification applied. For example, it's possible to select all feedstock, or it's possible to select a specific class, for example, primary biomass, or a specific category of primary biomass, for example, lignocellulosic from crops. The same for the product, and the same for refining technology. It's possible to select a specific class of technology, a specific categories, a country, for example, Italy. I select. It's possible to view the plant in Italy, a specific TRL, and so on. The selected features are visible in the maps, but also in the tabular form by scrolling down the windows. New tools appears above the table where it's possible to save filtered feature as shapefile, or it's possible to save filtered feature as CSV file. It's possible plot graph of filtered feature, or it's possible print filtered feature. Another very useful tool, and when a plant is selected, I'm selecting now this plant, for example, a pop-up windows will open where all information related to the plant selected are reported. imported, the name, country, city, owner, and so on. I come back to my presentation. Okay, all tools shown referred to the implementation of the web-GIS elaborated in the previous triennium. In this triennium, a new activity related to the web-GIS portal is being carried out. We can summarize the name of this activity is Update and Maintain Global Biorefinery Atlas portal. We can summarize the activity in new tools for proposing change, elimination of information of reporting and installation, and the provision of web app service and web feature service. Users want to use these new tools will have to register to the portal. In the new version of the web-GIS will be made available by the end of this year. Users who want to register on the portal will have to click on the highlighted tool. A pop-up windows will open where user must click on register here. A form will open where the information necessary for the registration must be entered. The information mandatory will be the email, password, and confirmed password. After filling the field and taking sign up, the system will send a confirmation email. User must click on the link sent by mail, and after confirmation, it's possible to access to the portal and use the new tools. In particular, registered user will be able to propose to modify the information associated to a specific plant, to propose to delete a plant, or to propose to add to insert a new plant into database and web-GIS tool. The tool delete, modify, and another tool that we call historical plant data will appear when a plant is selected in the pop-up window as shown in the image. This is the tool delete, this is the tool modify, and this is the tool historical. If a user would suggest to delete a plant, she will have to click to the specific tool. The system will store the request, which will be evaluated by the administrator of the web-GIS, that will be the national team leader of the task 42. The same for the tool modify. By clicking on the specific tool, a window will appear where all information associated to the plant are reported. After changing the information, by clicking send, the proposal is sent to the administrator. Historical tool is a tool that allows to view all the change related to the information reported for a specific plant. By clicking on the specific tool, a table will appear where the first row shows the data currently visible for the biorefinery selected, while the subsequent row shows the change to the data in ascending chronological order. In this way, it will be possible to follow the evolution of the data associated to a specific plant. With the function insert, the user will be able to propose to add a new plant into the database. After logging to the portal, a new tools will appear in the left subbar, insert new plant. A table windows will appear where user will have to enter the information related to the plant that they would like to include in the portal. Underlined in yellow-orange, you can see the mandatory data, the name of the plant, the source of the information, and accessed data. Underlined in red, the information could be chosen by a drop-down list elaborated according to the classification applied, and information can be entered as free text. After clicking Save, the system will store the request, which will be evaluated by the administrator. Other service that will be added to the portal will be the Open Geospatial Consortium service. It is an international consortium of experts which define the standard to be used in sharing geospatial data. In particular, the service that will be added to the portal will be the web map service, which is a standard protocol through which user can request georeferenced image, a raster, via internet, or web feature service, which is a standard allow user to directly request geographical object and not a map like web map service, which can be selected, queried, and so on. This service will be available by clicking on the highlighted tool. A windows will appear where user can copy the web map service link or the web feature service link. in order to guide user in these new tools. A guide in form of PDF flipbook and a video too will be added to the portal in a specific tool that we think to call. Thank you for the attention. Abuji, the floor is yours.
Costas, I think. Yes.
Or Costas, pardon.
Yeah.
Pardon.
Is it me? Yeah, okay. Just a second. Can you see my screen? Can you see my screen?
Yes, yes, yes.
Okay, so hello everybody. Thank you very much, colleagues from Enea, for this kind invitation. And today I will give some examples of catalytic hydrogenation processes that are being applied in biorefineries towards value-added bio-based chemicals and fuels. We had some introduction about biomass, and everybody knows that biomass has a lot of oxygen. So in order to produce purely hydrocarbon fuels, like from petroleum resources, we start by losing 40% of the feedstock. Of course, there are not only hydrocarbon fuels, but also oxygenated fuel additives like the compound I'm showing down here, which is the 2-methylfuran. And we can also produce some oxygenated chemicals that can be used for making polymers and plastics. In order to have a sustainable valorization of biomass and to be competitive with the petroleum-based products, we need to apply as many as possible of the 12 principles of green chemistry that Paul Anastas and John Gordon introduced a few years ago. And to name some is to develop atom and energy efficient conversion technologies. And here comes, for example, the utilization of the excess renewable electricity to produce green hydrogen, as we heard previously. Of course, to develop integrated biorefinery concepts, and by the word integrated biorefinery, we mean to be able to valorize the whole biomass, and not just fractions, just the cellulose or the lignin or the hemicellulose. And here, hydrotreatment processes, as you will see later on, play an important role as they regulate the oxygen content of the fuel and chemical products. Now, in our group, in Aristotle University of Thessaloniki, the last 10 or 15 years, we have been developing an integrated biorefinery, focusing essentially mostly on the selective fractionation of biomass. We try to apply neat green processes to separate the fractions of biomass. Initially, we separate the hemicellulose fraction, and we do different downstream processes to produce furfural, furfuryl alcohol, and other useful compounds. Then we work on the cellulose and lignin enriched biomass, where we convert cellulose to glucose and then downstream processes of converting glucose. And with lignin, we do different stuff, working directly on lignin as a polymer additive, for example, or by depolymerizing lignin to lignin biooils, and then doing some other processes for making fuels and chemicals. And here you can see that hydrotreatment is almost in most of the downstream treatments, as I'll show you later on, of course, along with other catalytic processes like hydrolysis, pyrolysis, condensation, and so on. Now, I focus always on the selective fractionation of biomass. And of course, it's always better to talk about waste biomass, as you see here on the left. So we have developed neat hydrothermal processes with a little bit of acid, where we selectively fractionate the hemicellulose part, and then glucose is produced via enzymatic hydrolysis to produce all these nice chemicals. And lignin, we are left with the so-called enzymatic hydrolysis lignin, where we do different processes there to end up with fuels and chemicals. Alternatively, instead of using just water, we add a little bit of ethanol, a very neat solvent, and this process is called organosolve. And via this process, we solubilize hemicellulose and lignin together. We leave cellulose alone on the solid, and then from this liquid, we precipitate lignin, and then we work on the recovered hemicellulose. So again, we have the three fractions separated. And again, I highlighted with yellow here some examples where hydrogenation applies. For example, I'll show you some nice data regarding sorbitol production from glucose. Let's start with the lignin fraction. What kind of hydrotreatments we can do? We can do direct lignin hydrogenolysis or hydrodeoxygenation of the lignin bioils. As probably all of you know, lignin is a recalcitrant phenolic biopolymer, as you see here, typical structures being constructed by these monolignals here, these phenolic units. And in our group, we work, as previously mentioned, we work on lignin directly due to its intrinsic reactivity. It has a lot of hydroxyls, carboxyl groups, and this makes it very reactive as an additive in polymers like epoxy resins, phenol formaldehyde, polyurethanes, and so on. But we also work on the depolymerization of lignin via fast pyrolysis and hydrogenolysis, producing bioils, which can then be upgraded further to cycloalkane fuels via hydrodeoxygenation. The hydrogenolysis, lignin hydrogenolysis, is a relatively mild process, low temperatures, liquid phase process, temperatures at about 250 degrees Celsius. Usually, solvent as a hydrogen donor is used to induce transfer hydrogenation processes like ethanol or isopropyl alcohol. And the aim here is to break the ether bonds in lignin and get a bio-oil rich in phenolic monomers or oligomers. The catalysts are typical hydrogenation catalysts like ruthenium, palladium supported on activated carbons, which are very robust supports. Here we see some data on the hydrogenolysis of Kraft lignin, which is a quite recalcitrant lignin. And we see that the bio-oil is enriched in oxygenated phenolics. And we have conversions up to 80%. But as you can see, the monomers in these bio-oils are quite low, below 10%. And if we look at the effect of reaction time, again, we have high conversions, mostly oxygenated phenolics, but the monomers cannot be above 20%. And this is due to the condensed nature of Kraft lignin. As you can see here, when we move to organose of lignin, which is a more reactive lignin, and when I'm saying more reactive, I mean it has more ether bonds, βO4 bonds. You see how the monomer yields increases from about 15 to about 30%. Now, biomass fast pyrolysis, a neat process, a nice process to convert biomass to bio-oil, fast heating of biomass, fast cooling of the vapors to increase the liquid products, the pyrolysis oil, and minimize gases and charcoal as much as possible. If you paralyze biomass, then the bio-oil is a very complex mixture of acids, furans, ketones, phenolics, and this makes it quite unstable, acidic, not miscible with petroleum fuels, and of course needs direct upgrading. However, if you pyrolyze lignin, the isolated lignin, then your bio-oil is more homogeneous and it contains mostly alkoxy and alkyl phenolics. These bio-oils can be and have been tested as a replacement of phenol in phenol formaldehyde resins, but also is a more homogeneous substrate for catalytic upgrading via hydrodeoxygenation processes. And to this end, we have done a lot of work both on model compounds as well as on real pyrolysis and hydrogenolysis lignin oils. For example, here is an optimization on the most simple phenolic, the phenol, with bifunctional nickel zeolite catalyst. We prefer to work with bifunctional catalysts and not the classical sulfide catalyst, the Nemo alumina catalyst. And you can see down here the mechanism. First, the hydrogenation leads to the cyclohexanol, and then further hydrogenation to cyclohexanol. Then the acidic support works here to have the dehydration towards the cyclohexane, and then again hydrogenation of the nickel to produce the final cycloalkanes. If we see the effect of the hydrogen consumption and pressure here, of course, if we don't have hydrogen, we don't have any products. But when we start from 30 bars of hydrogen, you see that the difference, if you go up to 70 bars of initial pressure of hydrogen, is not that big. That means that we can do a little bit of economy, hydrogen economy, for example, if we work at initial pressure of 50 bar. If we go to more complex feedstocks like light fraction, surrogate, light lignin bioil fractions, having these compounds inside, we can succeed again, very high hydrodeoxygenation degrees, high yields of cycloalkanes. The distribution of products are between C6 and C9. And some simple calculations here, you can see that we consume about 11 grams of hydrogen per 1 kilogram of bioil surrogate treated. And we talk here about 90% conversion of phenolics and 50 bar initial hydrogen pressure. So what this means that we started with about 14 grams of hydrogen per kilogram of bioil, and the outlet was 2.7 gram of hydrogen, meaning that we consume about 11 grams of hydrogen per kilogram of bioil. Now let's pass to the hemicellulose fraction, and more specifically to furfural valorization. The hemicellulose fraction usually give us xylose from most of the woods, and then xylose can be dehydrated to furfural. And if you can see at this scheme here, furfural is a very important platform chemical. It can give subsequent secondary platform chemicals, and finally monomers for polymers, fuel additives, solvents, a wide variety of chemicals. And then again here, hydrogenation is probably the preferred process to go through a furfural. You see at the first step, furfural is hydrogenated to furfuryl alcohol. Furfuryl alcohol resins these days are very important resins, trying to replace PF resins and other resins. And then depending on the catalyst, the reaction conditions and the solvent, you can see that we can have different reaction paths to different important products. For example, 2-methylfuran as a fuel additive, tetrahydrofurfuryl alcohol, 1,2-pentane diol as a monomer for making plastics, and several other very nice chemicals. Just very shortly here to see the effect of hydrogen, of the initial hydrogen pressure when we use a palladium carbon catalyst in ethyl acetate. You see, of course, without hydrogen, we don't have any conversion of furfural. And when we increase the initial pressure of hydrogen, we do increase a little bit the conversion up to 80%, but mostly we shift from 2-methylfuran to 2-methyl tetrahydrofuran, and actually we enhance the hydrogenation of the double bonds in the furan ring. So if you want to increase the 2-methylfuran chemical, you stay at a moderate hydrogen pressure. If you want to go towards complete hydrogenated products, you increase the hydrogen initial pressure. Quickly, let's go to glucose now, to cellulose valorization. And here, everybody knows that the second generation biorefineries and biofuels focused on the conversion of glucose from cellulose via fermentation to ethanol, but we can do also chemocatalysis on glucose, like hydrogenation of glucose to produce sugar alcohols like sorbitol and smaller ones, ethylene glycol and propylene glycol, with the appropriate catalysts. Why sugar alcohols? Of course, sorbitol, everybody knows, it's a sweetener. It can be used in many food products. Via dehydration, it can produce sorbital, a very important chemical to make pharmaceuticals and polymers. Via hydrogenation, it can produce very important monomers for making plastics, but it can also produce hydrogen via aqueous phase reforming. Now, the simplified reaction mechanism is the hydrogenation of glucose to sorbitol initially, and then inevitably, and again based on the catalyst, the reaction conditions, we start having some carbon-carbon rupture, hydrogenolysis reactions, leading to smaller sugar alcohols like ethylene glycol, glycerol, and propylene-diol. Of course, again, catalyst here is very important. Catalyst economy, noble metal economy is very important. That's why we try to disperse platinum and ruthenium as much as possible on the carbon and minimize the content of these noble metals on the catalyst. Some optimization work. For example, you can see here that the ruthenium catalyst is much more selective compared to platinum catalyst towards sorbitol. Whereas with platinum catalyst, you also produce smaller glycols. And again, more optimization here, we reduce the amount of catalyst over the glucose feed, and still you can see we have high conversions, high yield of sorbitol. And during the European project we ran at Aristotle University with another 30 partners, the aim of this biomass project is to start from the wood all the way to plastic parts for cars or for other commercial products. Here our role is to exactly hydrogenate glucose to sorbitol, and you can see that we have managed to produce almost 98% clean sorbitol at kilogram scale. And again, here you can see some hydrogen consumption for this process. Now, I'm quickly changing and closing with this from the lignocellulosic biomass to the lipid-like biomass. And of course, we're talking about the triglycerides. We need a lot of hydrogen to decarboxylate, decarbonylation, and hydrodeoxygenation to take the corresponding hydrocarbons. And here we have been working with microalgal lipids and also microbial lipids, working on the extractions and of course developing catalysts, as I said, bifunctional catalysts and not sulfided catalysts. For example, we have developed a nickel-based catalyst where we have about 90% and more of alkanes, minimizing acid and esters, and very importantly, with the appropriate normal to isoalkane ratio, you see here 80:20, this ratio being very important for fuel applications. Again, here utilizing our small micropilot reactor, we worked on microbial lipids during a European FlexiGreen fuel project, and we convert 100% the lipids to normal, corresponding normal hydrocarbons, and then other partners work on the isomerization towards aviation fuels. Now, closing some messages about the next steps in biorefining and hydrotreatments. Certainly, we need to utilize renewable green hydrogen or other types of renewable and environmentally friendly hydrogen. Of course, we need to develop more efficient and stable towards bifunctionality hydrotreatment catalysts. If possible and if applicable, depending on the process, to try to use hydrogen donor solvents and chemistry instead of high hydrogen pressures. And something that we are working on is to consider recycling and reusing the reactor outlet of the hydrogen-rich stream. Let me thank my group and my colleagues, collaborators, funding, and of course you for your kind attention. So the word is back to colleagues from MENA.
Thank you,
Oh, no,
Kostas.
it's to Abzit. Sorry. Yeah, Abzit.
So I'm going to start on my presentation, share my screen. And okay, can everybody see it? Yes?
Yes, 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 yes.
Okay, good, good. So yeah, so this talk is on two analyses that we did, and I'll talk about the details. My name is Abhijit Tata, and I'm from NREL, and I can advance. Okay, I'm basically a chemical engineer working on process modeling and controls in my past life with 30 years of experience. I do a lot of analysis on thermocatalytic conversion of biomass to gasification and pyrolysis. So there's a lot of details in this presentation, and obviously we can't convey all that in 15 minutes. So these two key references will give you a lot of details. You'll have a lot of questions, and you can, and of course, any analysis, it depends on the assumptions, and the results can change. So you can see all the details in these two articles that are available. They are open source. So the process focus of this talk is biomass pyrolysis, fast pyrolysis specifically, and also steam reforming. That's the second part of this presentation. Why did we do this analysis? So there are inefficiencies in any process. So obviously we would like to make as much liquid fuels and sustainable aviation fuels from pyrolysis processes, but that doesn't happen because there are inefficiencies. You produce gases, you produce char, and so on. So all those are also valuable, and they need to be exploited wisely to increase the sustainability of the overall use of biomass. And so the process resource, one of the things, key things, in this, especially the second part, is the off gases from fast pyrolysis and catalytic fast pyrolysis. And there's additional relevance to the analysis on the second part of it. You could use the same kind of analysis for other biogenic gases to analyze what happens if you put those gases into existing equipment for hydrogen production. And the methods, of course, are conceptual process modeling with heat integration. So as I said, again, basically any analysis is subject to assumptions, and please go through the assumptions before drawing conclusions for your choice of location, etc. So the first part of this talk is on locational infrastructure and decision making. So this was work that we did jointly, basically for a client. And so the question was, what do we do in this particular paper? We tried to answer, what do we do with the resources available? There are multiple options: electricity, heat and steam, fuel, gas, hydrogen. You could make them from the excess energy, or you could actually buy them from the, like electricity from the grid. So what are the smart choices in terms of the most efficient use of biomass? So in this case, as Kostas, the previous speaker, talked about, this fast pyrolysis was one configuration that we looked at in this study. And with that, as most of you know, rapidly heating biomass at nearly 500 degrees centigrade, it produces, so the major inputs are woody biomass, you have electricity, utilities, and the major outputs of that process are basically the biocrude, which again, Kostas implied that it's not it can be very reactive, and there's heat and steam and off gases. And also in terms of integrating electricity and utilities, you have electricity, steam, fuel gas. With catalytic fast pyrolysis, before condensation, you basically put it through a catalytic bed and or a fluidized catalytic system, and essentially improve the quality of that product. And in this particular analysis, we also had hydrogen feeding into the front part of the process. So the major inputs, in addition to what I talked about in the previous case, was also hydrogen, and hydrogen can also be a product in this case as well. So, and then this particular case, if you look at the reference, you will see that there were some chemical co-products, acetone and MEK in this case. So again, we are not focusing on the process itself. What we are focusing on is the utility integration options, which should carry through into other processes if you do similar analysis. So if you do look at a standalone biorefinery, then you have certain limitations. So if you export hydrogen, there has to be a consumer locally. Heat export, there has to be consumer, steam, fuel gas, similar gaseous exports, products. It's harder to transport gaseous products because of the volume. So you're limited in these aspects when you have a standalone biorefinery. Electricity export is flexible because the grid is everywhere and you are actually consuming electricity. You could put back electricity in the grid. With a co-located biorefinery, when you have co-located, meaning I'm talking about producing the biocrude and putting it in a petroleum refinery for final processing. When the biorefinery and the petroleum refinery are co-located or in proximity, then you have a lot of restrictions. These restrictions that I talked about go away, so you have much more flexibility in terms of using those utilities. So this particular analysis was for 2,000 tons per day woody biomass plant, and all the details. Many other cases are shown, but I just wanted to point out two particular cases. This was for the first one is for a standalone refinery, and let me remove this because it's interfering with your view, I think. So I can get this out of the way. Okay, so in the standalone refinery, as I said, electricity export is the most feasible in terms of flexibility. So in this case, I'm showing the CFP process, the catalytic fast process, and it shows how much energy is going in and how much energy is coming out in the different products, etc. And the second one is basically co-located facility with more flexibility. And this particular case, you could be importing hydrogen, you could be exporting hydrogen, you could be importing electricity. In this particular case, this is a favorable case from the results. Electricity import was included, and then this particular case had export of hydrogen, steam, assuming it was co-located. So based on that, we see, again, to point out the assumptions, the displacement method was used for all the co-products. The main product was a liquid biocrude. So using that method, we definitely see a benefit from exporting hydrogen and steam and importing electricity for the process. And also, we did the simultaneous economics for the process. So the summary of these two particular cases, and again, there are more cases in the paper. You can look at that. And so these are the costs and the GHG emissions. Moving on to the second part of the presentation. So we talk about making hydrogen. It is beneficial. What if it is co-located, and could you put that into a steam reformer, which is already making hydrogen? And can you get the benefits from less capital used in this process? So to answer that question that I had for a long time in my mind, I wanted to see what happens to the process itself if you put things into, of course, you could design a process to do steam reforming of the off gases, but what if you put it in an existing facility? So of course, in a steam reformer, you have two sides of it. There's a feed gas and there's also a fuel gas. So the fuel gas puts the heat into the process, into the endothermic reforming reactions. And the analysis, they included all the major equipment in the typical natural gas or steam reformer, including natural gas reformers. So there's sulfur removal, there's heat integration, there's a pre-reformer where you typically would take other molecules and try to make it as uniform as possible in terms of hydrocarbon that is typically processed in the main reformer. And then there's also water gas shift and PSA to produce the hydrogen. So as part of this publication, when we got the peer review comments back, they wanted us to validate some of that. And we used an IEA GHG report to look at the base case and see that whether they're comparable or not. And it turned out to be so, as mentioned in the paper. So really what we are trying to see is how do the key metrics start moving as you put pyrolysis gases into a natural gas reformer. Again, the composition of the pyrolysis gases assumed is in the paper. Really, we want to look at the key metrics. So CO2 emissions, that's our primary interest. How much does it move? How much of it is biogenic? How much is it possible as you start moving from 0% pyrolysis gas, which would be 100% natural gas, and then all the way to pyrolysis gases at the end. And then looking at all the key process parameters, I mean, so you have all the compositions start moving as you put in the gases, how much steam you make at different pressures changes, what is the reformer doing, what is the duty, and all that in the reactors, utility users, everything is tracked as you move through. And on the fuel side, this was only on the feed side, and at the bottom is the fuel side. You see a lot less impact on the process as you put in, use the pyrolysis gases as a substitute for natural gas as the fuel side. And so if you follow this, these lines, meaning the dashed lines over here, it's about 25% pyrolysis gases in the process. And again, this is a constant output of 5,000 kilograms per hour of hydrogen. Looking at this, you see that around 25%, when you put in around 25% on the feed side, you still are within the limits of typical over-design of processes, which could be around 15% or so. So you could actually get that much of pyrolysis gases without changing the design and changing the output. There are many other options you could use and to put in pyrolysis gases into an existing system, like cutting back your production and all that. But this is the assumption over here, maintaining 5,000 kilograms per hour. So we're looking at that. And then other key sensitivities in this study I'd like to point out is amount of CO2 that changes gas composition, and you could have a lot of that in say biomethane and stuff like that. So you could use that. Those kind of sensitivities are reported over here, and also steam to carbon ratio. And I'll talk about that in the next slide. So as I mentioned, you could put in 25% on the feed side within design constraints, and on the field side, you could go 100% without much changes. Then enabling CO2 as part of partial dry reforming could increase the efficiency, because you could put in less steam, and then that efficiency would increase, but then you would produce more CO in the process, and that might be beneficial if you're doing syngas conversion. Pre-reformers, if you take this kind of strategy, then your pre-reformer will play a critical role, because there are many gases and pyrolysis gases, as Kostas mentioned. Pyrolysis products have many compounds, and those could be homogenized before it goes into the main reformer, if you have a pre-reformer doing its job and converting those into typically methane and other gases. And then caveat, of course, this is a process model, and for an industrial implementation of this, there will be other considerations like corrosion, safety. There are supply design guarantees and stuff like that. So yeah, all those have to be considered. And as I mentioned, this analysis can be applied to other biogenic gases. So with that, I'd like to thank my co-authors for the first article, Michael Talmadge and Josh Hadley, and there's a lot of other people I thank for this. And with that, I'll end this and take, I guess we can all take questions.
Thank you, Abhijit.
Thank you.
Okay, thank you very much. Thank you very much. I think we have 2 or 3 questions for me, more or less. How Europe can develop a lower green hydrogen cost? I think we can't answer about that. We can estimate the integration with the bio-based industries of hydrogen, of green hydrogen, but we are not able to help about that. I'm sorry. Maybe we can ask to the hydrogen technical collaboration program of the IEA. Another question about the bioethanol production cost. We considered for the alcohol to jet process. I can remember it is a full plant So from lignocellulosic biomass to ethanol to sustainable aviation fuel. So we didn't estimate the only ethanol production cost, but I think more or less for only ethanol, we can consider from 0.7 to 1.5 euro per kilogram of ethanol. There was another question about the possibility to produce green hydrogen directly near the biorefineries by transmission and transportation of electricity, avoiding the green hydrogen transportation essentially. This is a good point. In general, I think the electricity is simpler to be transported. But the point is that green hydrogen is used as an energy carrier also to avoid the problems from the variability of the renewable energy sources. So maybe I don't want to push electricity into the distribution network, the electricity distribution network, but I can locally produce green hydrogen, maybe, and then I have to store and transport it. Maybe, but anyway, this is a point to the pin, sure. Isabella. I think. And I don't know if Isabella?
Okay, I think that Aristide, we answered to the major part of the question in the Q&A box. And I think that we are coming to the conclusion with respect to the time dedicated to this webinar. So I would like to thank everybody for this very large participation. And I also saw a nice dynamic discussion in the Q&A box. Sorry, I did a mistake in replying to some questions. And for time restriction, unanswered question will be replayed later. Well, I in general would like to share with you this consideration. I think that the integration of more renewable sources at local level to produce fuels and chemicals could really offer an opportunity to accelerate the green transition. Integration of the green hydrogen with biomass could offer also the opportunity for a novel nomenclature, not just biofuel or e-fuel, but why not e-biofuel? And this, at least in Europe, could be very important because could open perspective and stability to the biofuel industry in the future. I would like also to share some more discussion on this, but the time is limited. I also saw that some participants will attend the next biomass conference in Marseille, and this could be a nice occasion to meet and also to continue this discussion and to evaluate also the participation in joint research program. So thanks again for coming and have a nice evening. Bye-bye.
Bye.
Bye, Isabella.
Bye.
Thank you.